let's start off with what the problem says. It says that maximum length of a concatenated string with unique characters, which ultimately says the same thing, that we have to figure out, okay, we are given some strings. Again, the question itself is pretty vague, which means one edge case, the question, neither the question nor the examples cover what that is. Okay, we are given an array of string called as ARR, which means you can see array of string ARR, and a string S is formed by concatenation of a subsequence of ARR. I'll take some subsequence, which means I can take UN, UE, anything whatsoever, and then I can concatenate them, and you can see subsequence is just, but okay, any positions, any indexes I can take, and I can concatenate them and get the answer. But the condition is that it should have unique characters. So if I do a concatenation of them, it should ultimately have unique characters. Now, the one thing or edge case which you could have missed is, okay, do I need that, okay, both of them should be different, and after concatenation it can have a same character, or like after concatenation entirely, as in I'm saying, okay, let's say it has some element UN and it has IQ. So yeah, both have different, so I can simply concatenate them. I can make a UN IQ, and that will be my answer, which is the length 4, which is the maximum length, again, maximum possible length of S. But what if I ask you if it had a UN QQ? Then would you combine them? Because after combining, okay, you will say, because I'll just combine them because the characters are not matching. But for sure you will see that, okay, indirectly it's obvious that you need to have unique characters in a string, but yeah, it should have been specified at least in the example that we cannot take the string itself which has duplicate characters. That is one thing which you have to make sure. This is not mentioned in the question. Now let's come on that simply. We have to do one thing. We have to try the maximum possible length such that, okay, for example, if I am at the first location, I will have two options. Either I should take that character or I should skip that character, which means I just have to take some characters. I just have to take some strings out of this entire thing. It's a subsequence, right? So I'm just simply trying to make a subsequence. Subsequence is nothing but, okay, take it or not take it. So at this location, I have two options. Either I can take it or I can skip it. Then if let's say I take it, so I will have a CHA. Then I can go to the next one. I can take it, I can skip it. If I take it, I will have a CHAR. If I skip it, I will have a CHA, and then I can go on to next. So it's nothing but I'm trying to form all possible subsequences in the first place. Let's see, it's a simple take not take. Okay, take it, which means you will take your CHA. If you skip it, which means you don't take it, which means, okay, now you will have the new range, which is this entire range itself. Okay, let's say if you are at this location, if you choose to take R, then okay, you added a CHA and then R added. Again, I just wanted a subsequence. I wanted them to have unique characters, so I will have to maintain a check. I am not getting a string which is having duplicate characters. So that is check which will be applied if we are taking something. If we are skipping, simply skip. Okay, if we skip this, okay, skipping that, now the new range will be ACT and ERS. Now if I take it, if I take ACT, now you will see, if I take it, which means I will be appending this entire string on my CHAR. If I append this string, for sure A will actually match. If something is matching, your main condition that it should not have duplicate is violated. So for sure you cannot go here, which means you cannot take it. So for sure, if something I'm about to take, I will have to put a condition, okay, it's actually matching or not. Now if I don't take it, which means if I skip it, then for sure characters plus ERS. Now the same way the entire tree can be built. You, for your reference, you can have a look. But now for sure, as soon as your take not take comes in picture, we have a pre-owned mindset that we will apply DP. Right? Firstly, we'll apply DP. That is one thing you will think of. But in a contest, I'm saying in an interview, you might think of applying a DP. For sure, you might think, and that's obvious. But in the coding contest, you will see the constraints. DP is never used for these kind of constraints. Maybe we can use digit DP, but you can see these all are alphabets. So for sure, one thing is obvious. We have a conflicting views. One way we are saying that it's a take not take, which is obvious knapsack, which is obvious we can apply DP. Again, we have not gone through. Maybe you are smart. Maybe you are just saying, okay, for sure I cannot apply DP. But yeah, one thing is obvious, by our so much study that we might apply DP, and by this we see, okay, for sure if DP is not applied, recursion also will actually work, and that's obvious. Recursion will work with this kind of constraints. Very obvious. Because why recursion will work? What is nothing but 2 raised power n. A recursion is nothing but take not take. Take matlab you have two options. For every string you have two options. Take it or not take it. 2 into 2 into 2 into 2, and let's say you have n strings, so it's nothing but 2 to the power n, which will for sure work. So for sure recursion will work, but still let's see why DP cannot be applied. Now let's say if you apply DP, then DP will store a sub problem, right? And your sub problem and your main problem was finding the maximum possible length of string s. So your sub problem will also store the maximum possible length for a specific portion, which means let's say my sub problem stored starting from this index up till the super end what is the maximum possible length, right? Now let's say you will see maximum possible length right here is 4, which it can actually store. Okay, he will store 4 as maximum possible length. Then when I will be getting, like I will be triggering my answer for this portion, I will ask the pre-computed value for the right portion. For the right portion will say, okay, the maximum possible length in the right portion after this is actually a 4, which is the pre-computed DP value. So he will return a 4. But make sure while you are attaching the string, you had to make sure that your characters should not overlap. So you can only include the strings from here which don't have A, D, E and F, because this is the string having maximum possible length in this right part, which your DP will store. Now in this left part, which is okay, because as how a pre-computation work, like as how our top-down DP works, you will actually be landing onto this portion and you will use the pre-computed value of the right portion. And right portion will say, okay, maximum length is 4 and the string is A, D, E, F. So you can only take the string from here, which is actually not having a A, D, E, F, which is for sure you are going in a greedy way. So ultimately, the obvious counter example is that I had, let's say, a D, E, F, G, which for sure I cannot take because if I take it, then A, D, E, F, which was the maximum, and the right side, I could not have taken that. So I will have to pair it with A, B, C. Now, one thing we have to know, no matter what, I will have to store all possible combinations in this portion and then try it with all of the possible combinations in the left, which means ultimately, no matter what, again, many people will say, okay, I have written a DP code, but still, bro, your DP code will always have to keep all possible combinations. That is the reason your DP is not actually a DP. It's memorizing what? Like, so that's the reason. There's no technically, again, you can go and write that DP code and many people will just write for showcase, but that will not optimize your code because you will have to still store all possible combinations. Now, when this thing is on site, then we know, okay, we can simply apply recursion, and recursion is simple, take, not take. But while taking, make sure that you are not repeating, or basically your character should not repeat. So I'll simply have this array of strings which I pass, and I will start off from the index 0. Initially my string is empty. Now this string empty, which means my final string, my resultant string. Again, because of this recursion itself, you can actually, like in the interviewer asks you, okay, I don't want the actual string. I don't want the length. I want the actual string. So you can also get the actual string itself rather than the length. So that's a use case of this code also, that you can also get the actual string, which is having maximum length. Okay, cool, no worries. I'll have to start from the index 0 and go on to all the indexes. So it's a simple recursive case. Now we'll go on to the actual recursive case and then we'll go on to the base case. So firstly, if I have, let's say if I go back and I'll show you. So I have initially these all strings, right? These all strings. This. Initially my result is empty. As I showed you, initially my result is empty. I'm passing and I'm trying to build the maximum answer. So you will see, okay, initially whatsoever is the best result so far, just get that. And I have to try to maximize it. Maximize the two options, take it or skip it. Now, when I say take it, I will say, okay, current result, whatsoever I have built so far, if I am taking the ith string, add that string in my result, and I will get a new string, bigger string, and then pass it. And then say, okay, try for I plus 1, and then this is the new string which you are passing. If I skip it, which means I will just skip this AR of I, okay, I'll just simply pass the actual result itself and go on to my next index. This is the take not take, and whosoever give me maximum, I have to return that maximum. That is a simple recursive case. Now coming on to base case, again, remember, if at any point of time I encounter a string which is having duplicate, I have to return. Either you can return here itself, either you can have a check here itself, like here, while actually adding your character, while adding your AR of I in your string, you can have a check at this location, or you can have a check after adding. If you figure out later on return it. So now when I'm going back, now here I did, okay, I added that without even having like blindly seeing that I added that. But when I'm again coming, I'll check if my result has some duplicate characters. Bro, sorry bro, return it. I cannot have that. So he will just simply check, okay, the result set will simply, this is the actual string. Let's say if I had a b c, so my result set will contain a b c. So I just compare, okay, the length of my result and the length of my result set. Result set length is 3, result length is 4. What it means? It means that result is actually a string. This is actually a set. This will only have unique values. So I'm saying, okay, I have 3 unique values. He's saying, okay, I have 4 values. So for sure, one value is duplicate. So I'll just say if the set sizes are not same, I have a duplicate value. Again, there are multiple ways to compare. You can also apply a for loop, which is as same as this one also. So ultimately, if this is not matching, which means you have duplicate values, while if let's say it would have been only here, so the size would have been 3 only, so it would have matched. So that's okay. There's no duplicate. So if it is duplicate, simply return a 0. I cannot afford that. And worst, like for sure, normal base cases, you are starting from the index 0. What if you reach the end index? So if I just reach the end index, simply return whatsoever is the result size which you have got so far. Simply return that because it's a correct result without any duplicates. So this line should come after this line for sure, because I have to make sure I'm not returning something which is having duplicates. Okay, great. That's a simple recursion. Now let's see the time complexity of this. So if I just have a look, so I'll just show you that. You will see that, okay, one thing is for sure, in a simple recursion, what happens? You will actually be going on to all the cases. Now we saw that, okay, we have n strings, and different strings, and for each string we have 2 options. So for sure it is 2 raised power n. So my recursive loop will actually go to 2 raised power n times, which is okay, great, obvious. So this will try go to 2 raised power n times. But in this you will see there are few things which can actually increase the complexity, which means, okay, if it's a recursion, it's a tree, right? The depth of the tree will be nothing but depending upon I, which means, okay, he will try for this I, as you can see above also. Okay, this is the first index, trying for the first index, trying for the second index, trying for the third index of the string, like of the word. Like you have, let's say, this specific input as this ARR. So okay, first index of this ARR, next index, and this is the depth of my entire tree which I am making. So for sure, at every depth, I am trying to replicate or making a new string again and again. So what will happen in this is that at this location, if I have a character, so okay, character will be made. Now he will go down and character char, a new string. Okay, this is a string which was cha, will be made. Then when he will go down, he will make a new string char, because he know one thing, okay, I will have to maintain this cha, because what if I skip this r, then I will have to add a act later on. So he will be skipping, as you can see, he just copied this entire thing here, which means this was a cha. He will, again, how a DFS works, it will go in the entire depth. So right now he's not going here, but he's making a new copy every time. Cha, a new copy is char, then a new copy is char act. Let's say if it is actually made, but yeah, it's not made, but yeah, let's say if it would have been made, so a new copy. So now what will happen because of this new copy is that, okay, right now when he will go back, he don't have to return anything, he will just go back. Now while going back, he has stored this value in the memory char. So now he can easily go on to the right side, and he can easily try for the next one, which means ers. So you saw that, okay, at every depth I have to store the copy of this string. That is the reason at every depth, my depth is n, like my levels, like in time, my all the levels are n, and for every depth I am actually making a copy of the string. So for sure, at every level, which means n is the level for me, and for every level I'm actually making this copy of the string. So one thing is for sure, that I will have to add this complexity, which is n into w, in my actual string. So this n into w will actually be added, like apart from your this complexity of your recursion itself, which is 2 raised power n. You will have to do n into w. Thus you will see that again this n w is very small because n is 16, w is 26. So the multiplication is also a constant number, but still it will actually impact not much because the constants are very small. And the same goes for depth, that for every of the depth, n depth, you will actually be making a new copy of the string. So it is again an n into w which you will have added. So this will be time complexity and space complexity for you because of the copy which you are making. For sure, whenever some copies are being made, one thing we can obviously do is backtrack, which means you will not try to make a new copy every time. That is the reason of making a backtrack. Now what we will do by backtrack is, again, backtracking has two use cases. Going on to the previous value. Again, other use cases, just avoiding a copy of something. What we mean by that is, if I am having a CHA, I will just push again in the same string CHA. I'm not making any new copy. I'll push all the characters one by one of this upcoming string. Let's say the upcoming string is RA. Let's say upcoming string is RDE. Let's say RDE. So I'll push R, then D, and then E. So my entire push will be just nothing but, okay, pushing all these characters one by one in this specific string CHA. Now this will become RDE, the new string. Again, this is the actual string itself. It is not a new string. So CHA, the original string, I just pushed elements R, D, E, and then this has become a CHA RDE. Again, that is the only string. Now when going back, I know, okay, I added 3 characters. I don't matter what. I added 3 characters. R, D, E. I'll just remove 3 characters from the end. Okay, I'll remove R. I'll just remove 3 characters. That's it from the end. So it will just, while going back, it will land onto its original state, which was a CHA. And then I can go right side. And that is how backtracking simply works. Which means, okay, while going back, please revert to the original state itself, so as to try the next possibility. So I'll do a simple exact same thing. It's just that now my string is passed as a reference because I'm not making any new copy now, and I don't want to make the new copy. And the exact same base conditions, exact same thing. Is just that now the upcoming index word which I have, okay, for the ARR of I, for this all the characters I'll simply push back in my this result string. So I just pushed back all the characters of my ARR of I in the result string, and then I will just pass my result. But you remember, while going back, now this whenever you write any line below recursion, it is while going back. Now while going back, I make sure I have to remove number of characters which I had. So I'll just simply remove. Again, I'm not concerned about what the characters I added. I just have to remove all of them whatsoever I added. So I did it on the entire characters itself again, and then those number of characters I remove from the result itself, and then I will be very good to try on the next possible case. That is how a simple recursion will work. With this, you saw that it will actually and only go to the actual recursive cases, which is nothing but my exponential, my power n, which is this exact same time, and this entire operation will, again, you might say, Aryan, that is O of like a word size, which operation which you are doing on every characters. But yeah, that you will for sure have to do, because you will have to for sure try. So you can technically say, okay, O of W is being added at every call, which means that word size, which is actually 26. If you remember and go back, word size is the 26. So a kind of, in the worst case, a word size, which means every character is being copied again and again. So there can be O of W addition, O of W extra time added to it. That is okay, that is again obvious. But yeah, the space will be O of depth only. But yeah, you can also say, okay, at every depth, like at every depth of O of n, my actually word size might increase. So in the worst case, it can be O of n to W. That's also completely okay, but you will still see that via backtrack, the time complexity has reduced. Now comes the most interesting part. Can we reduce it more? Because you saw that the main weightage, or basically the main addition of time complexity was earlier it was because of the copy of strings being made. Okay, we reduced and we don't make any copies so far. Like we don't make any copies now, but still this string itself, which is being compared with other string, so this string itself is actually taking the time on every iteration, which means on every time, like I have to copy this entire string and then pass it and then compare it and all that stuff. This entire comparison of string actually happens, and this entire comparison of string will actually take the string length time. So, and this is actually O of n into W. So you saw, okay, my string comparison will take in time, my string comparison is taking time, my string copying is taking time. And why in the first place I need that? Okay, I need that because I will have to check. Okay, I can add ABC with DEF, but I cannot add ABC with ADF because A is repeating. So for sure, string comparison will be needed. If the string comparison is needed, and technically I have to just compare the string, and as I just have to compare, okay, if some character is matching or not in these two. Although comparison will be just 26 size, which is actually constant comparison, nothing much on that side. But yeah, still, if I am comparing something, and again, this actually will bound to OFW only, because you can have worst case 26 characters. Now coming on back, that you will have just 26 comparison, but still it's a constant increase in time. Can we reduce that also? Yeah, we can. How? If we see the constraints, it's a very small number. Now if I ask you that, can you just convert this entire string of length 26 to just one integer itself, and then the integer operation will be nothing but just comparison. So what I did was, okay, I will use bit manipulation to actually utilize this comparing, because I'm just comparing two strings. That is the main operation which I am taking, and I will have to add a string in other string. That's the time which I am taking right now, and basically it is more or less nothing but comparison or adding of string to other string. But I realized that my strings are very less size. I can use my bits to represent my strings, which means ABC I'll represent as a number as 7. So ABC as string, I'll represent as a number as 7. How? We will see that. So we will actually use bit manipulation. Now for sure, bit manipulation plus recursion, when bit manipulation plus backtracking, both will be same, because now I'm not even handling strings altogether. I'll actually use my actual bits, which means actual numbers I'll be using rather than my strings. So your recursion, we decrease the complexity by using backtracking, because we are actually modifying it, because we are actually not making a copy of the string. But now I'm saying I will not even make the string in the first place. Now coming on back, that how to actually convert the strings to integers is nothing but, we know we have 26 at max 26 alphabets, so we can assign all the alphabets just one bit. Okay, I'll say that A will be the 0th bit, B will be the first bit, C second, and so on and so forth. So if I am saying that, okay, if I have to mark that currently my one of these strings is actually A C D G, if my current string is A C D G, now to represent this string, I will actually be marking, okay, 0th bit, which means corresponding to A, mark that bit as 1, corresponding to C, mark that bit as 1, corresponding to D, mark that bit as 1, corresponding to G, mark that bit as 1. And with this I will get a GDCA. Basically you can imagine this as any combination. It's just that I'm concerned only about the frequency. For me, the entire sequence doesn't matter. I'm concerned only about the frequency. That's it. Because I just want to find the length. If you had to find the string itself, then there's a different case. Then you have to apply backtracking as the best option. But right now you're only concerned about the length. So this is the best option. That, okay, even if it jumbles, you are only concerned about the actual, what's the character, if the character is there or not. So what I'll do is, I'll take the existing example, I'll convert all of them to actually numbers. How? Okay, for the 0th bit, which means for the A, it is at the 0th bit, have a 1. For a B, have a 1. For a C, have a 1. For a D, okay, all of them will actually be a 0. D will be a 1. For a C, okay, it will be a 1. So I'm just converting all of them to actually my integers. And again, this is an integer value which is 7. This is an integer value which is 1 2 4 8 12. So this is how you can convert all this entire string as just an integer. But for sure, if you have something that's AAFG, now while you're converting that to an integer, so you will just mark the first bit as 1. You will mark the first bit as 1. Now again, next A comes in, which is, so you will see, okay, you already had a 1 and you are about to mark it as a 1. So for sure, this specific string, no matter whomsoever it pairs with, it will actually be making the answer as false. Basically, it will never actually contribute in the answer. Why? Because it is already giving me duplicate, which I never wanted. So he is giving me duplicate, which I never wanted. So for sure, remove him at the first place itself. Remove him at the first place itself. Okay, I'll simply remove him. Again, his approach also is super helpful in pruning. As in, like, although in Leetcode and all this stuff, you will just see, okay, it's actually useful in pruning only, but its main use case is reducing the complexity of comparison, and also it is very helpful in pruning. Pruning means, okay, if you have a recursion tree, Let's say if you have not watched the 100 days 100 days placement series, in that I have discussed pruning, but in one of the problems of backtracking itself, which was generate parentheses, because in that we will not generate a specific part of the tree, which is actually called as pruning. In that, what we will do is, okay, if we know this is the entire tree which will have, I will cut some branches that he will never go down in these branch. I'll cut these branches itself. So with this, what will happen is it will never go and try for this comparison. So my entire tree branch will actually get reduced in the first place itself. Now I'll convert this also to actually integer, and that's how I can actually do it. So if I just show you that how this comparison is done, you will go on to all the characters. You'll go on to, again, you will make a character bit set. This is a character bit set, which is actually an integer I showed you. Now you will go on to all the characters, let's say BDF. Now as you go on to all the characters, you will have to make a mask. So initially my entire thing is a 0 0 0 0 0. A number 0 is actually a 0 0 0, 32 bits, right? Okay, again remember it is 32 bits, and integer is 32 bits. Okay, that is great. We have 32 bits. Now as soon as I encounter first character, which is actually a B, so I will have to make sure, okay, B is there, right? So 0 0, let's put it as like this, 0 0 0 0. So I need to know that, okay, A B C. So I need to know, okay, first index, first bit, I have to mark it as a 1. So I will make a mask as 1 0 0 0 and so on so forth, and then I'll do a OR operation. So what will happen with this? Or again, you can just have a quick check, and then you can do OR operation. Again, OR operation and AND operation, if you don't have any overlap, both are same. So okay, I can do an OR operation or an AND operation. Again, if you don't have an overlap, what I mean by overlap is 1 plus 1. 1 plus 1 is actually a 0 1, but 1 or 1 is actually a 1. So if I say 1 or 0, this is an OR sign, a straight danda, it's actually a 1. 1 plus 1 plus 0, again it's a 1. So when you don't have any overlapping bits, or an AND operation, both are same. Remember that fact. But still, here we can also apply OR operation. But you remembered, we need to have a quick check if some bit is not repeating. So firstly, before even applying an AND operation or an OR operation, I'll do a quick check. I'll do an AND operation and check if that specific bit was 1 or not. If this AND operation comes as a non-zero value, which means, okay, if this is a 1, so he will come 1, and remain all will for sure come as 0, because your mask have all of them as 0, and you are doing an AND operation. So for sure, if this is a non-zero, which means I have a repeating character which was already set. So okay, if the character bit, which means this character bit set, and the mask which you have made, this is a mask, this is a character bit set. If the AND operation is some non-zero value, simply return, because you have found a string which is actually having duplicate characters in itself only. Okay, great, no worries. But if not, then you can simply do an OR operation or an AND operation. Both are same. Again, I told you how. Now, so if you remember, it was actually a 0, so he will actually become a 1. Now my new character set is actually this thing. This is my new character set. Character bit set. But you remembered, I have just passed one of the characters, B. I have to next pass A, so I'll pass my A. I'll simply make a mask. Okay, sorry, this was a 1 and this was a 0. I'll simply make a mask which is nothing but 1, and all of them are 0. Then all of them are 0. Let's erase this. Now I'll simply do a OR operation again. Firstly, I'll have a quick check. But yeah, if I do OR operation, I'll make a 1, and all of them are 0 again. This is my new character bit set. Now again, A is done, do a F, so I'll make a mask of F, which is 1, and then some zeros here. So I'll again do a AND operation, which means, sorry, OR operation or a plus operation. Both of them are same. So I will get a 1 0 0 whatsoever was there, 0 0 1 1, and that will be actually representing this specific string as an integer. Again, if I get, this is actually all the work is being done on an integer. So you will see 1 left shift C minus A. C was actually in the first place, your first character was B. So your first character was B. So B minus A is nothing but a 1. So you are left shifting 1 time. Left shifting 1 time. If I say, okay, if I have a 0 0 0 0 and a 1. So this is, okay, 1 left shifted 0 times. If I do a left shift of 1 time, so he will become like this. If I do a left shift of 1 2 times, he will become like this. Okay, this is how my left shift works. Now this is how you know, okay, how your strings will be converted to an integer. Now, but do you remember one thing, what you wanted? You wanted to know the maximum length, which means that you will also have to store the length. Now, if you have any string, let's say if I have this string, I want to know the length of this string. I know any character is not repeating, so all of the characters are unique, right? So I know that if I have some bits as 1, so for sure they are contributing uniquely in the answer, which means I will have A one time, B one time, and F one time. So one way is that, okay, in this integer, I can just count the number of a set bits, which are actually 3. That will give me the length of the string. But if the integer is n, counting the set bits take log into the base 2 time, because you just have to go into all the bits of that integer. Integer has 32 bits, so counting the bits in an integer of length, like of 32 size, like an int, it will actually be 32 in the worst case, which means, okay, to count the set bits, to just get to know the length itself of this specific string, I'm using a log n operation. That is very less, but still my entire constraints were actually 16, 26, which are actually less than 32. So for me, log n also is also a contributing answer. So I should actually remove this also. How I will remove this? I will say how I'm maintaining. Okay, I have A, B, and F. I will also parallelly maintain if what is the length. How and where? Again, I just have one integer. I cannot use multiple. I can use, but yeah, that will increase the complexity. But yeah, I use only one integer to populate this value also in the same integer. How? Let's see. That is so interesting, no? Yeah. So what we will do is, okay, we know that we will have at max 26 unique characters. So this length will actually be at max 26, right? So, and we remembered we have 32 bits. So for sure, 6 bits are still remaining for us to utilize. So what I will do is, I will get this length. It is a 3 length is 3. I will left, again, length is 3 is represented as 1 1 in binary form. I left shift this number 3 26 times, so that it never overlaps with the first 26 characters of the English alphabets, and then I will populate this value after 26 bits. So now the starting 26 bits will represent the characters and their frequencies, and the remaining 6 bits, and in worst case you will remember, okay, the length can be 26, which is actually nothing but 32, which means which is less than 32, and 32 is 5 bits, so it is less than 5 bits, or basically you can say 5 bits at max, which we can for sure store because we have 6 bits remaining. So this is how that is so interesting, So again, that is this mesmerizes me. So what we will do is, again, if you tell this to an interview, I swear I'll hire you at the first place. I'll hire you. Cool. Now we are storing, okay, in the starting 23 bits we are actually storing the frequency, and the last bits 6 bits we are actually storing the length. And the same way we'll do for all the characters. Okay, for him I'll reserve, again, no matter what, I'll reserve the starting bits for my characters only, and the last bits for my length. Okay, you will see the length was actually a 2, so I represented a 2 here, 1 0. Here the length is 3, so I just put a 1 1. Now in the same integer I have both the string with the individual frequencies, which means, okay, the string with the actual contribution to the answer, and also their length. Now just nothing but, again, while comparing you will have to bring back these numbers, which means if I want to compare these two strings, I will have to bifurcate, which means I will have to get this entire stuff out, which means I have to get this entire blue part out from this, and the purple part out. I have to get this part out, which is actually a work, but yeah, it's worth it. Now let's quickly have a look at how we will actually be making this entire string. Okay, from this string, how I will make this number. I'll simply, as I showed you previously also, to make this starting blue part, which is the first part, we will simply use the same operation as we saw above also, that we'll go into all the characters, we'll make a mask of all the characters. Let's say if I get a C, so I'll make a mask as 0 0 1 and all our other zeros, which means 1 left shifted 2 times. What is 2? Nothing but C, which is a character minus A. Again, C is the actual character here, while C is the iterator here, which means, okay, C can be A, B, C, and so on and so forth. It's just a variable. But right now I'm saying C is actually actual C. Here it can be D, which is D minus A is actually nothing but a 3. Same way, I'll iterate on all the characters. I'll make a mask first. If the mask and my actual this character bit have any bit as like overlapping, which means any bit is actually already set, then I'll simply have to return. If not, then I'll simply do a or and plus operation, just simply adding the bits. But I also remember I have to also get the length. I'll firstly get the length from my nothing but from my input, which is the specific word which I'm trying to get the mask of or get the int of, and then I will have, okay, I'll just left shift this length to length 26 times. I will get this new mask, which is nothing but 0, like which is nothing but 0, 0, 0, 26 times, and then this is the length, which is again 0, 0, 0. So this is the new mask of the length. So I'll just get the length bit, and then I can simply add this, or you can also do the or operation here. Again, or, and this operation, or, which is bitwise or plus, bitwise or plus, both are same in this case because we are not having any overlapping bits. So remember this fact, but yeah, that can be confusing if you are relying on this entire array. Now, have a quick check that how the comparison will look like. That let's say if I have this as a specific result. Now, if you remembered that in the entire recursion tree, we will have some result and then we will be comparing with the ith index. A simple comparison, how it was done. So I know that, okay, I've converted this actual result, which means this actual string to actually a result, which is an integer. But I know the starting 26 bits represent the actual characters, while the last 6 bits represent my length. So I will make sure to actually compare if the characters are same or not. I will have to compare the starting 26 bits only. Again, I cannot iterate on those 26 bits. Then still it will actually land to the same condition that we are iterating on those 26 bits. I cannot do that. So what I will do is I will get this 26 bits out, which means I will make a mask. How? I will make a 1 1 1 1. I just see, I now ultimate my main aim or my maqsad is to get these 26 bits out from this number without even iterating on them, all of them again and again. So what I will do is I will make a mask which is 1 1 1 1, all that stuff, and then remaining all of them will be 0. What will happen with this is if I do an AND operation, so for sure all of them in this left part will become a 0 and all of them in this part will become whatsoever was in the input. So if I make a mask of 1 left shift 26, which means 1 left shift 26 times. If I do a -1, then again this is 0, which is 26 times. If I do a -1 with him, he will go 0 and all of them will actually become a 1 of length 26. So we will have a 1 of length 26. Now with this a 1 mask of length 26, I will be doing an AND operation so as to get only the starting 26 values of the input. So I'll get only the starting 26 values of the input and the remaining values will actually be a 0. So this is my original result ABC. But now you also will repeat the same process for this specific I, and you remember you have firstly did a pre-computation and converted all these to an you converted all these to an integer, and you just stored that in your ARR as bits. Let's say you name the vector as ARR as bits and you stored that in a vector. Let's say for him the value is you will see 1 2 1 it is 1 2 4, so it is actually 7 plus this values which is 2 to the power 20 and something. So this is okay, like you stored an integer. Okay, this is integer value, integer value, integer value, integer value. This is integer values. Now you will get this integer value from your ARR of as bits. Again, from this also you will have to extract out the last 26 characters. You will make a mask for the last 26 characters, which means 1 1 1 1, and then you will do a AND of these bits. Again, this is the reason bit manipulation is not easy for everyone. If you are not familiar with AND operation, mask and stuff, it will be hard, and that's the first place I was not about to teach you these methods. But I thought that why you should not know the most optimal approach. You should know because no one has taught this. Yeah, why? Cool. Going on back. So firstly we'll have, again, if you're liking it, then please smash the like, baby. Cool. So we will make this mask of 1 1 1. We will have this ARR as inputs, but we want to extract only the last 26 bits. We'll do an AND operation. We'll get the last 26 bits at itself. Now to know, okay, we have got this original result. Now we are about to compare with this specific. I need to know if they have same characters or not. The same thing which we did here, which we did right here also. If you remembered, I'll do and go back. If you remember, to go and check if something has same bits or not, you just simply do an AND operation with them. So here I want to know if this specific bit was set or not, basically originally was there or not. I did an AND operation. If the AND operation gives me a 1 value, which means a non-zero value, again it is not a 1, this is actually value 2 in integer. So if this gives you a non-zero value, which means for sure you had repeating characters. So same way what I will do here is, I know my ABC is represented as 00111, so I know I have 000111, which is ABC, and then this mask is nothing but 1000 and 011, which is actually nothing but my ABF. So you will see if I do it is ABF, yeah. So if I do an AND operation, this everything will become a 0. So you saw that the contribution of F became a 0, the contribution of C became a 0, but B and A both were repeating, so both contributed something. So I can only attach two strings if they don't have duplicate values. So what I will do instead is, I will just do an AND operation. If this value is 0, I am good. I can add this incoming character, incoming index, which means this specific string I can add in my original string, which was this ABC in the first place. I can add that. But if it is not, you can only skip that. So if the AND operation gives me a 0, only then I should try adding that. And when I say add that, simply again, I'm concerned about the length. So simply, firstly, add both of them. Again, here also the OR operation will work, right? OR operation will work. Here OR operation will not work. Here AND will work, because you are adding two lengths. You converted, okay, you got the length, which is 2, you got the length, which is 3. Now you are adding the length, physically adding the length. Now the new length will actually become 5, and then you converted that to binary form, and then you placed it. So here the OR will not work, here the OR will work. This is the reason I told you the implementation of basically how the OR and AND changes. Now here, because you know here also OR and AND both will work, because these new characters and old characters, we made sure that they don't have any duplicate characters. Only then I am actually adding them. So what will happen now? For this case, it will actually not be attached. But if I take the other example, let's say if I take my other string, let's take the other string, let's take this string. So if we have a CD, we have a BAF. So if I convert the CD, I'll grab the only characters, last 26 characters, I'll grab them as a bits. Okay, that is a number 1 2 4 8, which is 12, and this is the length, which is actually number 2, which is nothing but as a 10 in bits form. So this will be a 10, number is 2, this is a 1100, which that number is 12. And the same way I'll convert this BAF, okay, nothing but it is saying some number. Let's say the new characters, it is 10011, again integer value you will get to find out, and here is the new length, which is nothing but a 1, integer value is 3. Now I know that my final answer, I will have to get all these characters. So I'll just do a OR operation, which means 1100, and I will have a 1100 and 1, right? So I'll simply get a 111101, which represents I have a A, I have a B, I have a A, I have a B, I have a C, I have a D, I have a F, and you will see I have a A, I have a B, I have a C, I have a D, I have a F, and that's how I can simply represent it. And again, the values, which means the length, it is nothing but 2 and 3. Adding that, I'll get a new length as 5, because for sure every character was unique, so I'm just simply adding the length. My new length is 5, but make sure that the characters should again occupy 26 bits, and the final length, which means the length which you have made, should go in the last 6 bits. So left shift the new length, which is 5 by 26, so as to move that to left. Remaining starting space of 26 characters should be of characters, and length should be the last 6 bits. Thus you can simply get the new result. Thus this is the only modification which you need to do in the recursive code. First is pre-computation, and next is using that pre-computed values. So first you will see that I will convert my all. So again, you will have a quick doubt on why we are using AR of bit set. So basically we are using unordered set of AR of bit set. Now you will have a question that why unordered set, why not vector and stuff, and why we're converting a vector, but we will solve all that stuff. So firstly, we are just getting AR of bit set and it is nothing but an unordered set. So it will store for all the strings their corresponding integer values. And when I say string, I am storing starting characters, 26 characters, as the actual frequencies, which means that the actual occurrences of the characters, and the last bits, which are 6 bits, we are actually storing the length. Now this is the function word to bit set, which will convert this specific word and push it, or basically insert that into my AR of bit set. Okay, how this function will work? This function, as I showed you already previously, it will go on and make this character bit set, right, which is keeping the occurrences of all the characters, go on to all the characters of that specific word. Let's say the word here is just ABC. So he will actually try to make, firstly he will have to verify if that is already not there in the mask. If not, then he will actually make a actual character bit set will actually become a 111 and all the bits are 0. But you remember, we also have to add the length in the next 26 characters, which means after skipping the starting 26 characters, I will have a length bit set also, which is nothing but a length mask, which will be after 26 characters, which means I will have a length. Let's say the length is here 3. I will left shift that 26 times. I will get a 1 1 and 26 zeros, and then I will do a OR operation, or basically a plus operation, anything. I'll get a new mask, I'll get a new value, which will be nothing but I'll insert that in my AR of bit set. I am passing this by address, right? Okay, I will insert. So basically it's something but corresponding to this specific word, I got its integer value, which is having occurrence and length combined in one integer, and pushed it into my ARR bit set. But it might happen, firstly, I will never be storing, if something is like AABC, this will never come inside my ARR bit set, right? Okay, that will never come. But what could have happened is that if I had used vector here, then something as ABC, and if ABC is still repeating in my actual ARR, if in ARR I have ABC twice, then this, if I would have used a vector, then I would have made his integer, let's say his integer value will be X and his integer value will also be X. So my X would have been twice. And there is no point whatsoever that you can have two duplicate values or two duplicate strings. So a two duplicate strings entirely is not even use case for us. So here also we just use a unordered set rather than a vector to do again a pruning. Again, there's another pruning which is happening here by avoiding duplicate strings at the first place. Here we avoided duplicate characters, but here we are avoiding duplicate strings. So I got this in my unordered set, then I converted that to a vector, and just, okay, all the values of the unordered set, which only will have unique values representing unique strings, I will convert that to my AR of as bits, which means now it's a vector. So as to iterate on the vectors, because we have to iterate on the words itself, I converted them to a integers, and that I stored in the vector, which is an array. Now I'll simply call the same recursive function. Now in the same recursive function, just a simple thing, that the actual result which you have, existing result, you will grab out the actual occurrences of the characters and the length, and the new incoming ith index, you will grab out the actual occurrences and the length, and then you will try to match it. So in the existing result, I grab the old characters whatsoever I had by simply saying, okay, whatsoever is existing result, and by simply making a mask of 111 26 times. So I will get only the last 26 actual character in my result. And I'll get the old length, which is nothing but, okay, whatsoever you have the result value. Let's say if I have the result value is 1 1 and all are, let's say, some values, some 26 values. So I want to truncate these values. So I'll just do a right shift, which means this 1 1 will be right shifted 26 times. So this all will be truncated down. 26 times it will be all truncated down, and this I'll only get this specific length. So I'll got this length now. So currently my best possible length is my current own length, which whatsoever I have. That was the input also, the result length. Now the simple base case, if my I goes beyond, then simply return the best length you had possibly here. But if not, then find the new characters in this AR of as bits of ith index. I'll find the new characters again the same way we did here, same way we will do here. Now I will actually have to go on and check that, okay, I am trying to attach these new characters in my old characters. I'm trying to attach that, right? So I have to check, okay, if these should not overlap. Now for that, I'll simply have a check. If these don't overlap, only then I should add my new characters in my old characters. I'll simply add that, and this is the same operation which we did, finding the new length, finding the new result, which will be nothing but old characters plus new characters. Here also I can apply OR operation, but this will be new length plus old length, and then left shifting 26 times so as to move it back. So this will be my length, which is in the last 6 bits. Again here plus or both will work, but here plus will only work. Now coming on back, we will have the best answer, which means maximizing the best answer, and try to solve it for the next index considering the new answer only. But no matter what, you can have other case, which is the not take case, which means simply go on to my I+1 with the actual existing result value, and then ultimately returning the best possible answer. With this, your time and space are exactly O of 2 raised power n, but with extra pruning at many levels, which will actually increase, or basically which will actually reduce your complexity by many times, just because of that you for the bigger strings you are pruning a lot. And that's how it will be much more efficient. But in complexity terms, it will actually be like representing these values, but it will be much better. Cool. Thanks for watching. I know that the video is 51 minutes, but I want it, like, this is just a test. That's the reason, like, I mostly skip in DP problem also. I mostly skip the very much, let's say if I am teaching a DP problem, I know that bottom up will not optimize the code, but still I skip that bottom up code because I know that people are mostly concerned about, okay, I should solve the problem, that's it. No matter what the complexity is, no matter what the analysis of the problem is, no matter how it is useful for you or not, people just want to skip it. And that's the reason we have less views, because of long video length. And again, the video will go on around 10:30, which is way too much time, and usually the people push the video around 6 a.m. or 7 a.m. We will be pushing around 10:30 a.m., which is actually way lot. So to make this entire notes and stuff, it took time, which actually will implicate or replicate, or basically will actually affect the entire thing, video reach, video, like, interaction and all that stuff. But still, I wanted to have this as an example for any of the further bit manipulation, recursion, and or backtracking videos, because this was the first problem involving everything. So that's the reason I just went into it. If this gets good response, I'll probably try to discuss every approach in all the videos. But going forward, I make sure I only discuss the approaches which are actually reducing your complexity. Cool. Thanks for watching. Goodbye. Bye bye.